All right, this is the second in 3 videos on word problems. I'm working through the practice test 2 for 2021, and I'm going to now do question 6. All right, let's read the question. Let x of t be the amount of bacteria in a water treatment tank at some time t. So from that sentence, we know our independent variable, and we know our dependent variable. Because we're going to make an ODE, we know that we should be looking for an ODE of the form dx dt equals something, right? And when we read the rest of the question, we'll find out the contributions to that rate of change of bacteria in the tank. So we can start by writing down dx dt equals something, and we can look at the contributions to that rate. So suppose the water treatment plant has a chemical that removes bacteria, right? So that's a reduction, it's negative contribution, from the water at a rate proportional to the amount of bacteria present at any instant in time. So that's starting to look like an A constant times X term. However, we've got more information. But the efficacy, represented by the constant of proportionality of the chemical, decays in time like 1 over t. So whilst it's a bit of a clumsy way of putting it, we're going to have a term removal, and that term's going to be negative because it's reducing the rate of bacteria, or it's removing things, so it's negative. We've got a constant, but then that constant sort of changing, like it's not really constant. The the term that multiplies this x of t, the amount of bacteria. So remember that this is just amount. Every time you see amount of bacteria, that's an x and t. This a term decays like 1 on t, so that becomes an a on t, or alternatively, it's an a times 1 over t times x of t, like that. Right, so that's what our removal term looks like. So this removal, as time goes on, as time gets very, very big, there's less and less bacteria being pulled out of the water. That's what this says. So as t tends to infinity, the removal term tends to 0, right? So obviously this chemical is being consumed, it's being used up, or it's becoming, like, the bacteria is becoming resistant to it. So that's another way to think of it, right? So this chemical isn't as effective over a long period of time as it could be. Suppose that the rate at which new bacteria, so now we've got stuff coming in, so we've seen the magic word rate introduced, I guess, is the in, is constant. The rate at which bacteria, new bacteria is introduced to the tank is constant instead of depending on the bacteria's population, right? So that's to contrast with question 5, where we had bacteria that reproduces. So we've got bacteria being introduced into this tank somehow. So, so I guess here's our tank. Here's our little bacterium jumping in, and that's happening at some constant rate. So we've got an introduction term, and that's just constant, so let's call it K. No t dependence, no x dependence, nothing. It's just constantly, there's a constant flow of bacteria creeping into this tank. But we assume that the bacteria is small enough and the rate is small enough that this doesn't actually change the volume of the tank. Right, so our rate, our dx dt, that has the removal and the introduction. So dx dt equals minus a over t x of t plus that constant k. Now this is a linear first order ODE. We need an initial condition to solve for a particular solution. And in here, finally assume that the initial amount of bacteria in the tank is 0. So whatever's coming inside the tank, or it's physically, this might represent the decay of some sludge in the water supply. So like you've got some bacteria in sludge that's like creeping, that's the source of our bacteria, it's creeping in that way. But our initial condition is x of 0 equals 0. So there's nothing originally in the tank, it's all flowed in afterwards. This is a linear problem. We can rearrange it to the canonical form. Like so. We can now deduce the integrating factor. So our integrating factor is this integrated and exponentiated. So it's going to be r of t equals e to the integral of a on t dt. Integral of a on t is a log of t. So I'm assuming that t is going from 0 and becoming more positive, so I don't have to worry about the absolute values. I don't need a constant of integration because that'll just divide out in the wash anyway. This is log t to the power of a using our log laws. And then finally, we can use the fact that log and exponential are inverse functions. I can't just invert the function here because I haven't dealt with this a yet. I've got to put that a up in the power before I can like say, well, I've got an e applied to a log, so that's just going to give me the argument. Right? Now, once I've got this integrating factor, I can multiply my equation by it. T to the a dx dt plus a t to the a over t x t equals k t to the a. Now I can use what some people term the reverse product rule on this, collapse it down. Right, we've seen this in lectures. We know why this happens. It must always happen because of the form of our integrating factor that we've selected. And we now have a problem that's directly integrable. This side can be integrated with respect to t, the left-hand side, and the right-hand side is trivial to integrate with respect to t. So let's go ahead and do that integral. Let's integrate this bit to get t a x to the x of t equals, integrate this side with respect to t, we add 1 to the power and divide by the new power. So that is k t to the a plus 1, that's adding 1 to the power, divide by the new power, a plus 1, and we've got to account for a constant integration, plus c. So we're nearly there. Because we're going to have issues with t equals 0, if we divide through by this, we'll apply the initial condition now. So x of 0 equals 0, and this fairly obviously implies that left-hand side 0, k on a plus 1 times 0 plus c. So c is equal to 0, courtesy of our initial conditions. Finally, we want to rearrange this expression here for x of t on its own. And we can obviously cancel out the t to the alpha here and here. And we find k a plus 1 t. So what's happening here is that the growth of bacteria in the tank, the number of bacteria in the tank grows linearly with time, right? And it grows linearly with some tx, right? The intercept is 0. The gradient here, the slope of this line is k on alpha plus 1. And so if k is large, then the number, like our bacteria, gets big quickly. If a is large, then if a is large relative to k, I should say, it'll grow more slowly like that, right? So that represents, the strength of our bacteria killing chemical is encapsulated in the A, but you know that it's getting weaker as time goes on. It gets less effective at removing the bacteria. And K is the growth rate of is the rate at which bacteria is introduced. So obviously, like if your chemical's getting less effective as time moves on, and the amount of bacteria coming in is constant, then obviously, your bacteria is going to grow over time.